In 2015, a star in the constellation Cygnus dimmed by more than 20%, a drop far deeper than any planet could cause. The light curve was erratic, with no clear rhythm. Headlines exploded with one speculative idea. Could it be an alien megastructure? A vast construction built to capture starlight? But scientists found the key. The dimming was chromatic. Blue light faded more than red. That pattern doesn't fit a solid object, but it perfectly matches tiny particles of dust. In 2015, astronomers spotted something nobody could explain: a star in the constellation. Cygnus dimmed by more than 20%, far deeper than a planet crossing its surface could cause. Headlines quickly asked, could this be an alien megastructure, like a Dyson sphere? In plain terms, a megastructure is a hypothetical, artificial construction built to capture starlight, and the Dyson sphere was first proposed by physicist Freeman Dyson as a thought experiment. It was always a hypothesis, not a conclusion. The discovery came from NASA's Kepler mission, which monitored more than 100,000 stars between 2009 and 2013. Nearly a decade later, the data still raises questions. In this video, we'll cover three things: what Kepler revealed, how astronomers tested competing hypotheses, and what the evidence today most strongly supports. With that groundwork set, let's look closely at the star that first showed this puzzling behavior. The star that shouldn't dim among the thousands of stars Kepler monitored, one case quickly demanded attention. Catalogued as KIC 8462852, a technical identifier from the Kepler input catalogue, it dimmed by as much as 22%. In exoplanet studies, even a planet the size of Jupiter usually reduces its star's light by only about 1%. A drop more than 20 times that amount suggested something more unusual than a planet passing in front. Astronomers also noticed that the dimming did not follow a regular schedule, but varied in both depth and timing. The signal lacked the neat, repeating rhythm seen in planetary systems, instead showing irregular patterns. That behavior immediately raised questions. The unusual light signature was first flagged not by a professional team, but by volunteers in the Planet Hunters project. These citizen scientists, reviewing Kepler's brightness plots, noticed the strange dips and passed their findings along. Astronomer Tabitha Boyajian and her colleagues then confirmed the dips were genuine features in the data, not errors from the spacecraft. Because of her leadership in the analysis, the star informally became known as Tabby's star. To put the mystery in plain terms, astronomers study what's called a light curve, a graph of a star's brightness over time. For a typical exoplanet transit, this curve shows a smooth and repeated dip, steady brightness, a short decrease when the planet crosses, then a clean return. But in the case of Tabby's star, the curve looked different. Dips ranged from less than 1% to over 20%, and they came without any consistent spacing. It was an erratic pattern not explained by planets alone. At that point, some references circled back to a decades-old speculative idea in astrophysics. Physicist Freeman Dyson once proposed, as a thought experiment, that an extremely advanced civilization might build vast structures around a star to harvest its energy. Such Dyson spheres were always framed as a hypothesis to illustrate possibilities, not as predictions for a specific case. In theory, fragments of such a megastructure could cause starlight to dim in irregular ways. On paper, this resembled what Kepler had recorded, but it was never supported by direct evidence tied to KIC 8462852. The connection to Dyson's work captured media attention, and headlines began suggesting the signal could be an alien megastructure. Yet astronomers were careful to emphasize that science requires eliminating natural explanations before entertaining extraordinary ones. Light curves by themselves cannot reveal what, in physical terms, is blocking photons before they reach the detector. A range of natural possibilities remained plausible, from clouds of dust to swarms of comets breaking apart. The consensus approach was to test every idea systematically, rather than leap ahead to more speculative conclusions. Even so, the lack of an immediate match to known phenomena kept curiosity high. The Kepler spacecraft had run extensive checks for instrumental noise, and the results held up. That meant whatever was happening was genuinely astrophysical, not a glitch. For researchers, the problem became how to investigate such a puzzling source with better tools. Without follow-up data, the dips remained a set of unexplained signatures on a graph. Because the dimming events showed no predictable rhythm, waiting for the star to act up again became the only way forward. The challenge was clear. The next time the star's light dropped, astronomers needed to be ready to observe it across different wavelengths with multiple instruments. That realization set the stage for the next phase of research, when telescopes around the world coordinated in the hope of catching the phenomenon live, chasing the mystery in real time. Astronomers soon realized that the only way to make progress was to watch the star in real time, tracking every dip as it unfolded. Kepler had recorded the mystery years earlier, but to test competing ideas, researchers needed fresh observations across the spectrum. In 2016 and 2017, campaigns began that aimed to keep the star under continuous watch with an unprecedented level of detail. The photometric follow-up drew on several instruments working together. Las Cumbres Observatory, a global network of robotic telescopes, provided round-the-clock optical coverage by handing off observations from one location to the next as Earth rotated. NASA's Spitzer Space Telescope added monitoring in infrared light, which is especially good at piercing through dust. At the same time, the Swift Space Telescope gathered ultraviolet measurements, giving scientists a view of higher energy radiation. By combining optical, infrared, and ultraviolet data, astronomers could check if the dips looked the same in every band, or if the star behaved differently at different wavelengths. That question, whether the dimming treated all colors of light equally, was what investigators most wanted to test. Public attention peaked during these campaigns. Media outlets repeated speculation about alien megastructures, while astronomers emphasized that such exotic ideas remained only a hypothesis and that natural explanations had to be tested first. Even so, the possibility of something artificial raised one more line of inquiry. If advanced technology existed around the star, could it leave a detectable signal beyond mere brightness changes? This is where the search for technosignatures came in. A technosignature means any measurable sign of technology, such as a very narrow radio signal unlikely to occur naturally. Human systems often use narrowband radio transmissions because they carry information efficiently. That made it reasonable to at least check if Tabby's star showed anything similar. In 2016, the SETI Institute trained the Allen Telescope Array in California on the target. This specialized array of radio dishes scanned a wide range of frequencies for months, listening for narrowband signals that would stand out against the natural hiss of cosmic static. The result was a null detection. No narrowband signals, no repeating transmissions, nothing that could be identified as artificial. It is important to note the limits of this result. The search covered specific radio bands with particular sensitivity, but did not rule out all possible forms of technology, or signals emitted on different frequencies. In other words, the absence of such signals narrows the options, but it does not completely close the case on artificial activity. Even so, this provided a clear boundary. If an alien megastructure were blocking the star and releasing radio transmissions in the bands the array could detect, those signals should have appeared. Their absence meant that strong, narrowband radio technosignatures were not present. This pushed researchers to look again at natural explanations, returning focus to the star's light curves themselves. The combination of real-time monitoring and radio silence illustrated the careful, step-by-step method of science. Researchers explore bold hypotheses, test them with available tools, and use the results to refine what comes next. With alien radio signals now an unlikely explanation, attention shifted back to how the dimming itself behaved at different wavelengths of light. That wavelength dependence, the question of whether blue light and red light faded equally, was about to become the central piece of evidence. The next set of observations would supply the turning point that finally gave astronomers a clear direction forward: the breakthrough of chromatic dimming. The evidence that changed the debate came in 2018, when astronomers identified a distinctive pattern now known as chromatic dimming. In plain terms, chromatic means the dip depends on wavelength, or color, while achromatic means all colors fade by the same amount. For Tabby's star, the dimming was not uniform. Blue light dropped more strongly than red. That unequal behavior provided a crucial clue because it meant the cause could not be a solid structure simply blocking the star. The discovery came from monitoring the star across several color bands at once. Using multi-band photometry, instruments separated the star's light into channels, blue, green, red, and measured how much brightness changed in each. Spectral measurements supported the same result. Every time the star dimmed, the blue channel showed the steepest drop. That color dependence was the key observation. It gave astronomers hard evidence to test against the competing ideas. Here's what the data show. Solid objects such as planets or hypothetical megastructures block light evenly, regardless of color. That effect is known as achromatic dimming. By contrast, very small particles scatter light unevenly, with blue affected more than red. On Earth, this is why our atmosphere makes the sky appear blue. Tiny molecules scatter short wavelengths more efficiently than long ones. The same physics suggested that fine-grained dust, orbiting in front of Tabby's star, could account for the uneven dimming. In one concise sentence, grains smaller than visible wavelengths scatter blue light more strongly, and that scattering produces the chromatic slope seen in the data. The implications were clear. Chromatic dimming strongly contradicted the idea of a massive, opaque structure crossing the star's line of sight, whether natural or artificial. If large panels, satellites, or a Dyson-like array blocked starlight, the outcome would have been achromatic, with all wavelengths reduced equally. Because the actual data showed the opposite pattern, astronomers gained confidence that dust was a far more realistic explanation. This did not mean every detail was settled. Several hypotheses remained about the origin of the dust. Some researchers proposed it could come from evaporating comets releasing fine particles. Others suggested collisions of planetesimals or fragments from a disrupted ring system. While uncertainties persisted, the consensus was that small particles were responsible, regardless of their source. What mattered was that the color-dependent signal matched dust physics and did not match solid objects. The breakthrough mattered in two ways. First, it provided a straightforward method to separate natural explanations from exotic ones. By checking not only brightness, but also color, astronomers could spot cases where unusual dips might be due to dust rather than something more extraordinary. Second, the result balanced public interest with scientific caution. While media attention had amplified the alien option, the actual chromatic data redirected the search back to natural sources. Science showed its strength by following measurable evidence instead of speculation. Chromatic dimming thus became a boundary marker. It showed the star's behavior fit with ordinary physical processes and strongly reduced the plausibility of an opaque megastructure. While no observation can eliminate every possibility, the specific pattern of blue light scattering left little space for large, solid constructions around the star. What remained was the task of pinning down which natural process best explained how dust reached and moved through the system. By shifting the frame from speculation to testable physics, the 2018 observations gave astronomers a new starting point. The largest part of the mystery was no longer whether machines orbited the star, but why dust appeared in irregular and sometimes dramatic patterns. That question became the guiding focus for the next phase of research: natural causes and future searches. The current consensus among astronomers is that the puzzling dimming of Tabby's star is best explained by circumstellar dust or exocomets. Circumstellar dust means tiny particles orbiting the star that scatter light unevenly, and an exocomet is a comet-like body in another solar system that sheds gas and dust when warmed. These small particles naturally match the observed chromatic dimming, where blue light fades more strongly than red, and they can shift and disperse in ways that produce the irregular timing of the star's brightness changes. One leading hypothesis is that families of exocomets are breaking apart. As they disintegrate, their tails release fine dust clouds. Because these fragments are not bound in neat, repeating orbits like planets, the timing of dips in brightness would be erratic, aligning with the irregular light curve. Their microscopic grains also scatter shorter wavelengths more effectively, so the dips reveal the chromatic signature identified in 2018. A second plausible source is collisions between planetesimals, the rocky or icy building blocks of planets. When these bodies impact each other, they throw debris into surrounding space. As clumps of fragments drift across the star, they create variable dimming with no fixed repeat cycle. The small grains released by such collisions again explain why blue light is absorbed more than red. This makes planetesimal collisions another way to meet both the timing and wavelength conditions of the data. Some more speculative hypotheses have also been proposed. One involves disrupted ring systems. If large ring structures once orbited a planet and were destabilized, the resulting debris could scatter into complex configurations that pass in front of the star. Irregular shadows would then appear, and if the material is made of fine particles, it could produce chromatic dimming as well. However, this scenario lacks direct supporting evidence and has received less agreement than comets or planetesimal collisions. Another weaker hypothesis is intrinsic stellar variability. Some stars naturally flicker due to internal processes in their outer layers. But Tabby's star does not fit any known class of variable stars, and its variations persist over timescales that variable star models struggle to explain. Moreover, stellar variability would not easily create the strong color dependence observed. For those reasons, this explanation remains unlikely compared to dust and debris. All viable models must satisfy two constraints: the timing of dimming events and the chromatic signature. Dust produced by exocomets or collisions fits both, whereas mechanisms like stellar variability do not. That combination of requirements has kept dust-based explanations as the leading interpretation. Testing these ideas requires two main observational tools. Transit photometry tracks the total brightness of stars over time, building long light curves that reveal when dips occur, how deep they are, and whether any regular patterns exist. Spectroscopy, by contrast, divides starlight into its component wavelengths to show whether dips are chromatic or achromatic. Spectra can also reveal chemical fingerprints or the effects of particle size. These methods in combination let astronomers compare competing hypotheses and narrow the field to the most plausible causes. Future surveys are expected to expand our ability to test these models. NASA's TESS spacecraft, launched in 2018, continuously scans wide sections of the sky for brightness changes. Its coverage increases the chance of identifying other stars with similar dimming, which would help determine whether Tabby's star is unusual or part of a larger group. Soon after, the Vera C. Rubin Observatory in Chile will survey the entire southern sky on short cadences, creating a long-term database of variability and transient events. This enormous record will provide the comparisons needed to place Tabby's star into broader context. By now, the picture has shifted from speculative to practical. Dust clouds and comet fragments may sound less extraordinary than an alien megastructure, but they fit the data more closely and highlight how science builds certainty. Every observation trims the list of possibilities until the explanations that remain are the ones supported by evidence. That steady process not only resolves mysteries, but also shows why careful testing is essential when claims first appear extraordinary. And in this case, the story does more than solve a puzzle about one faint star. It shows how evidence has the power to cut through speculation, guiding research toward explanations that stand the test of observation. Conclusion: the consensus today is clear. Fine circumstellar dust best explains the strange dimming of Tabby's star, not a giant structure. Three main observations led here: the irregular timing of dips, the chromatic dimming that showed blue light was blocked more strongly than red, and the lack of narrowband radio technosignatures in the bands searched. Together, these results point firmly toward natural causes. This matters because it shows why science must rule out natural explanations before proposing technology. Tabby's star remains a valuable case study in how to approach responsible searches for technosignatures with evidence-first discipline. Let us know in the comments which part of the investigation you found most surprising, and subscribe for more evidence-first space explanations. Key takeaway: the data favor dust, not an alien megastructure, and upcoming surveys will test that conclusion further.